Hello everyone, this is Chayo John from Manchester Metropolitan University. I would like to introduce our work, Reverse Masking Network, a perceptual adversarial network for image inpainting. In this paper, we propose the R-MNet, an end-to-end framework for facial image inpainting. We extend our network to natural scene images by training on Places 2 and Paris Street View datasets. We achieve perceptual similarity by using a new combination loss function that focuses on the missing regions and the valid ones. We use different weights in the form of coefficients on the reverse mask loss to investigate its effectiveness. We show that our method, implemented with reverse mask mechanism, can improve the quality of inpainting. Here is the overview of our RMNet framework during training. It has a generator which is composed of an encoder-decoder network and a Wasserstein discriminator that measures the quality of predictions with the ground truth. These networks are jointly optimized end-to-end. The green arrow shows the reverse masking operator and the red arrow shows the spatial preserving operator. During training, RMNet takes two inputs, the mask and the image, and computes the convolutional input, the masked image. We implement the reverse mask loss using matrix operands that reverses the mask during training. During training, the mask is reversed in a forward pass to the end of the convolution where it is added to the convolutional output. Following the arrows to the left, you can see here the mask is reversed with matrix operands and transferred to the end of the convolution, shown in dotted lines. The reverse mask is then added to the convolutional output, thus forcing the convolutions to focus on predictions of the missing regions. To compute the reverse mask loss with access to the reverse mask mechanism, we concatenate the mask to the final output of the network. The reverse mask loss via backward pass ensures that the network focuses on predictions of the missing regions, yielding predictions that are consistent with the entire image. We use the spatial preserving operator to gain access to the mask image. We define the reverse mask loss using the mean square error space. We ensure that our reverse mask loss targets only the valid features created by the mask during reconstruction. By using the mean square error space, we target the square difference of the corresponding pixels specific for regions created by the mask on the image and the reconstructed pixels of the mask image. To achieve perceptual similarity, we use the best combination weight on the feature loss and the reverse mask loss. To show the effectiveness of our reverse mask loss combined with the reverse mask mechanism, we conducted an ablation study. We applied different weight coefficients between 0 and 1 and obtained the results on the table and the figure. To blend the predicted pixels with the entire image, we started by giving a very small value of lambda. We noticed a poor performance visually. This is because our mask has masks of different sizes, which will take longer for the network to learn larger corrupted regions. This means the bigger the mask, the longer it will take for the network to achieve perceptual similarity, thus being computationally exhaustive. We made changes to the value of lambda until we achieved a perceptual similarity. Our network strikes a balance with the weight value 0.4 on the reverse mask loss. For training and testing, we used the Select AHQ dataset and split it according to the state of the art. As masking method, we used a quick draw dataset by Iskaskov et al. With max whole to image ratios ranging from 1 to 60%. Our result outperformed the state of the art quantitatively and qualitatively. Our results are shown in bold. Visually, when we compared our result with the state of the art, we found out that the output image from our model is closer to the ground truth than the state of the art. To conclude, we proposed the reverse mask loss jointly optimized end-to-end using WGAN. We demonstrated that our model can perform image inpainting. We showed that our model can compete with the state of the art. And we've included in the slides and on our paper a GitHub link where you can find the repository and the resources to test and train our model. Thanks.